Hi everybody, we are on to Unit 5, which is integration, and today we are going to do integration day 1, and we'll start off with what's called the antiderivative game. And it says, I give you the derivative, you guess which function has this derivative. Sound fun? Okay, so now we're kind of working backwards from differentiation. So if we have the derivative of 2x, we have to think to ourselves, okay, what original function has that derivative? And you might be able to see that it would be x squared, right? Because if we took the derivative of that, the 2 would multiply down in front, and then it would be replaced by a 1. Okay. So the original function must have been x squared. Okay, plus any constant though, right guys? Because the derivative of a constant is 0. So the derivative of x squared is 2x, and the derivative of any plus c would just be 0. So that's the type of function that would give us a derivative of 2x. Okay, if the derivative was 3x squared, that comes from x cubed plus any constant. Right, the derivative of x cubed would be 3x squared. What about this one, 9x to the 8? That would actually come from x to the 9 plus c. Okay, if the derivative is 3, the original function must have been 3x plus any constant. And then they can get a little bit tougher. Like, for example, if the derivative is x, we'd have to have x squared with a 1/2 in front plus c, because 2 times a half is 1, and then the power of the x would go down by 1, and we would just get x. If the derivative is x cubed, the original function, if the derivative is x squared, the original function would be x cubed with a 1/3 in front plus c. If the derivative is 7x to the 4, we'd have to have x to the 5 with a 7/5 in front. And so maybe you're starting to see the pattern here. Okay, so if the derivative is x to the n, it's kind of like doing the reverse power rule. We have to go backwards rather than multiplying the exponent in front and then subtracting the exponent by 1. What you have to do is add 1 to the exponent and divide whatever is in front by that new exponent, and then plus c. And if there's some other constant in front, same deal. Power goes up by 1. Whatever's in front is going to get divided by that new power. And then, of course, we still have to have plus a constant. I'm going to put C1 just to differentiate that from that C constant that's in front. Okay, look at the formula we have developed. Okay, let's graduate. So let's say the derivative is this big expression. You just do each term one at a time. So the original function, if we have x squared, the power goes up by 1. You take that new power, divide whatever is in front by that new power. For the next term, it's x to the 3. So it would become x to the 4, and whatever's in front, the negative 12, is going to get divided by that 4, so it'll be a negative 3 in front. And you can always check by differentiating as well. Four times negative 3 is indeed negative 12. Power goes down by 1. Okay, next term here. we are going to get x to the 6. And then notice we have 1 over 2, and we have to divide that by 6. 1 over 2 divided by 6 is equal to 1 over 2 times 1/6, which is 1/12. So we're going to need a 1/12 in front there. 6 times 1/12 is indeed the 1/2 that we would get right here. Okay, and that's 3x to the 0, so it becomes x to the 1, and then 3 divided by 1 is still 3. So that's what happens with those constants. And then, of course, we need plus any constant on the end. Okay, 1 over x squared. I would first of all write this as x to the -2, and then do the little thing where you add 1 to the power. Whatever is in front is going to get divided by -1, so it puts a negative there, plus c. Okay, which you could also write as -1 over x plus c. The square root of x is x to the 1/2, so if I do the antiderivative, I would have to add 1 to the 1/2, which would take us up to 3 over 2, and then we'd have to go 1 divided by 3 over 2, and then plus c. Okay, 1 divided by 3 over 2 is 2/3, and we get x to the 3 over 2 plus c, like that. Yeah, so what I did there was 1 divided by 3 over 2 is equivalent to 1 times 2 over 3, and so that's where I'm getting the 2 over 3 out front here from. Comes from this calculation. And finally, this is x to the 4 minus x to the -3. And when we do the antiderivative, we are going to get x to the 5 with a 1/5 in front. And then we will get x to the -2, and see how we've got that -1 over -2 plus c. So this will be x to the 5 over 5, and that is plus 1 over 2, and then it's times x to the -2. If you wanted to, you could flip that down so that the power becomes positive. So we could write it like this. Okay, and so this is called finding the antiderivative or integrating. Now, just as we had notation for taking the derivative, we will have new notation for taking the antiderivative. Remember some derivative notation? There was like this prime symbol, ddx. Okay, and what that means is take the derivative with respect to x. Okay, I'm just going to pause here for a second. Okay, and so antiderivative notation looks like this. It looks kind of like an elongated s. It means the integral of x squared dx. And it means find the antiderivative with respect to x. Okay, so yeah, like the dx part is sort of saying that you find the antiderivative or the integral with respect to x. Okay, I'm just going to pause again here for a second, guys, because there's somebody going by with a lawnmower. All right, so evaluate each integral. The integral of x to the 4 dx, so what do? You add 1 to the exponent, whatever's in front gets divided by your new exponent, and plus c. 5 times 1/5 is indeed 1, and then x would go down to x to the power 4. If we took the derivative of this, we would get back to x to the 4, so everything is good. This one, the power on the x goes up to 8, and 5 over 8 plus c. Okay, and this one here, 3x squared, we would go x to the 3, and then 3 divided by 3 would just leave a 1 in front. The x to the 4th would become x to the 5 with a 1/5 in front. Negative 2x would become negative x squared. And positive 3 would become plus 3x with a plus c on the end. This next integral, that would become x to the 5 with a 1/5 in front, minus, this would become x to the 2, and then the negative 3 in front would get divided by 2. And this little expression here, 2 over x squared, is 2x to the negative 2. And so the power on the x, you add 1 to it, right? So it goes up to negative 1, and then the 2 gets divided by negative 1, which would put a negative 2 there, and plus c on the end. We could leave it like that. You could flip the x to the negative 1 down so that it becomes x to the positive 1. This next little integral, the integral of just seemingly dx, there's a secret 1 there, which is actually 1 times x to the 0, so the power on the x would go up to 1. 1 divided by 1 would remain as 1. So it's really just x plus c. The derivative of that is 1. Okay, and this last one, this would be the integral of 1 over x to the 1/2 dx, which is the integral of x to the negative half dx, and then we add 1 to the negative half, which is a half, and this 1 in front gets divided by that new power, and then we go plus c. 1 divided by a half is 2, so it's 2x to the 1/2 plus c. Okay, and you can leave it like that, or we could write it as 2 root x plus c. Okay, and so that brings us to page 3. Now we have several integral formulas we could write down formally. The integral of x to the n dx, it's like reverse power rule. The power would go up by 1, and whatever's in front gets divided by that new power, and plus c. If you are taking the integral of a constant times a function in x, and you're taking the integral with respect to x, you can actually divide the constant out and just do the integral of the function part. If you're doing the integral of two functions added together, you can split them up, which we've already done. You do the integral of f of x dx plus the integral of g of x dx. And the integral of a constant with respect to x is c times x plus some other constant, possibly. Right, the derivative of c1 would be 0, the derivative of c times x, the derivative of x is 1, so it would just leave you with c. Now, for some integration, you have to do a bit of thinking or working. So, evaluate something like this. Oops. The integral of x squared plus 1 all squared. Remember what this means. It is x squared plus 1 times x squared plus 1. And if we multiply that out, we would get x to the 4th, and then you would get plus x squared and plus x squared, so plus 2x squared plus 1. Okay, so a little bit of working, and then it's a simple integral from there. We would get x to the 5 with a 1/5 in front. We would have 2/3 x cubed, and then plus x, and then plus c on the end. Okay, with this one, what you have to do is take the x to the 4th on the bottom and split the fraction like this. Divide the x 4th into both terms, right? And then we would get the integral of x to the 2 over x to the 4 is x to the negative 2 minus 2 like so. And now we're ready to do this integral. That would become x to the negative 1 with a negative out front minus 2x plus c. All right, how about the integral of x times the square root of x? This is the integral of x to the 1 times the square root of x is x to the 1/2. And you know how 1 with a denominator of 2 would be 2 over 2? So we would be going, when you multiply two powers with the same base, you add the exponents. So 2 over 2 plus 1 over 2. This would be x to the 3 over 2. Oops. And then we have to add 1 to that exponent. You have to go 3 over 2 plus 1. Which is 3 over 2 plus 2 over 2. So it'll become 5 over 2, and then you have to divide this 1 by 5 over 2 here and have plus c. And of course 1 divided by 5 over 2 is 2 over 5. And there's our integral. And finally, the last one, let's multiply this through, and we would get the integral of x plus 1 over 2x cubed and flip that exponent up. And now we are ready to integrate. And we would get x to the 2 with a 1/2 in front, x to the negative 2 with a negative 1/4 in front, plus c. Right, where did I get the negative 1/4 from? Because I had to take this 1/2 and divide by negative 2, okay, which makes it negative 1/4. Okay, and so we could leave it like that. All right, and so then it says sleeping yet? Because hopefully that's pretty easy. Evaluate these. What is the integral of cos x dx? Where we have to say, okay, what original function would I have to have that has a derivative of cos x? Well, that was sine x plus c. The derivative of sine is cos. And this is saying what original function has a derivative of sine x? That would have to be negative cos x plus c. Because actually the derivative of cos x, remember, was negative sine x. And if you have this extra negative out front, then it would make it positive sine x. Okay, so that's why it has to be negative cos x plus c. And what we'll do is we'll consider all of the basic trigonometric differentiation formulas. So remember, the derivative of sine x is cos x. We can put a little dx beside it, saying we're differentiating with respect to x. The derivative of cos x is negative sine x dx. The derivative of tan x, remember, was secant squared x dx. The derivative of secant x is secant x tan x. The derivative of cosecant was negative cosecant x cotangent x. And the derivative of cotangent is negative cosecant squared x dx. Okay, and so now we can use these formulas to work backwards. These differentiation formulas above lead to these integration formulas. So the integral of cos x, you can see up above there, is sine x plus c. The integral of sine x, see, notice that we've got this negative sine x. You have to just kind of take the negative over that way and go. The integral of sine x then is negative cos x plus c. The integral of secant squared x would get us back to tan x plus c. The integral of secant x tan x, so if we look up here, if I integrate secant x tan x, I would get back to secant x plus c. The integral of cosecant x cotangent x, see how there's that negative sign, would have to be negative cosecant x plus c. Okay, and the derivative of cosecant squared x, notice that we've got that negative again, so it would have to be negative cotangent x plus c. Okay, and so these are some nice trig integration formulas. Okay, so now we can evaluate these integrals. The integral of 2 sine x is going to be negative 2 cos x. And the derivative of 3 cos x will be plus 3 sine x plus c. Okay, and then of course we can differentiate this expression in the box to see if we get back to that original. Right, the derivative of cos x is negative sine x times negative 2 would give us the 2 sine x. The derivative of sine x is cos x times 3 gives us that. And the derivative of a constant is 0, so that works out. The derivative of the integral of 4 cos x is 4 sine x. And the derivative of secant squared, the integral of secant squared x is tan x plus c. This one, the integral of 3 secant x tan x is 3 secant x. The derivative of the integral of negative cosecant squared x is cotangent x, and then plus c. So, do you think it could get harder? Evaluate these integrals. And for these, some of these guys, we might need this little formula sheet with trig identities and things, and I'll send this to you as well. Okay, so if we look at the first one, the integral of sine 2x over cos x, look on our sheet here, right there, sine 2 theta is 2 sine theta cos theta, so you could just replace the theta with an x, and so we can go like this, sine 2x is equivalent to 2 sine x cos x, divided by that cos x, and then dx. And then the cos x's will cancel, and it's the integral of 2 sine x dx. Okay, and we have to say, all right, what function has a derivative of 2 sine x? Well, I think that would be negative 2 cos x plus c. Okay, the next one is the integral of basically 1 over secant x dx. What is secant x? If we go and check this out right over here, secant x is 1 over cos x. So we could say that this is 1 over cos x. But 1 over cos x would just be cos x. So it ultimately is the integral of cos x dx, which is sine x plus c. How about this one here? Got to do a little bit of work with this. We're going to write this in a special way. 1 over 1 over sine x times cos x over sine x. And 1 over sine x is cosecant x, if you go and check this out right here, right? And cos x over sine x is cotangent x. Right, if we check out our identity sheet, cotangent theta is cos theta over sine theta. So cos x over sine x is cotangent x. Okay, and the integral of cosecant x, cotangent x, we have a formula for that. It is negative cosecant x plus c. Okay, so really, like, the only way to know to do that is to just make sure that you know these trig formulas really well, to kind of maybe look for these types of forms in different trig expressions. Okay, what about this one? For example, if we multiply this through, we would get cosecant squared x plus cosecant x cotangent x. And both of those expressions show up above, right, in our integral formulas. The integral of cosecant squared x is negative cotangent x, and the integral of cosecant x cotangent x is negative cosecant x with a plus c on the end. This integral, let's factor out the top. They have sine x in common. So if I factor out the sine x like that, it leaves me with x squared plus 2 on the top. We also have x squared plus 2 on the bottom, just in the opposite order, so those cancel to 1. So this breaks down to the integral of sine x dx, and that integral is negative cos x plus c. And then finally we finish off with the integral of tan squared x. Now we don't have a formula for tan squared x, do we? If we go back to our formulas, there is no tan squared x. So that means identity sheet. Tan squared shows up right here, right? 1 plus tan squared x is equal to secant squared x. So what we would have to do here, guys, is just get tan squared x by itself. Subtract 1 from both sides. Okay, so tan squared x is equal to secant squared x minus 1. Do we have integral formulas for secant squared x and minus 1? Minus 1, certainly. Secant squared x, hey, right there. The integral of secant squared x is tan x. Okay, so the integral of secant squared x is tan x. The integral of negative 1 is negative x plus c. Okay, so that is integration day 1. There's an assignment here from the textbook that you can try. Answers should be on my website in the integration folder. And there are some additional integration questions here as well, with an answer key at the bottom. Okay, so there you go, guys. Let me know if you have any questions, and we can go from there. I'll talk to you soon.